see. Hello, and welcome. I'm outside again. Um, 2 days ago, we talked about an experiment, or you can call it an activity if you like. And this was for my math class. And thank you so much for helping me. Your support was really meaningful. So today we are revisiting those two activities from I can't say from pre-calculus or calculus point of view. Really, it's from any angle you prefer. First of all, it was not easy for me to see your comments from the phone while we were doing those exercises. Only if you came through, but then later on, after I turned off the live session, I saw your comments. And today I wanted us to focus on the most prevalent feedback that I got. A few of you said the exercise was better represented as a displacement time graph, but you didn't tell me displacement in what direction. So I had to answer my own question, which is not fair. So for those of you who missed the exercise, first I made a demonstration. I was 87 years old. I was running or stopping and that kind of a thing. And in the second activity, I was 17 years old and I just trotted for about a minute or so. And that movement was rather constant and predictable. So those were the two activities. And I just wanted to provide you that feedback in case you don't know what we're talking about. But you're welcome to look at the video on my Facebook wall. And I wanted to focus mainly on your feedback on the presentation of the graph as a displacement timepiece. I agree with you, although I feel like you short-circuited this exercise somewhat because you didn't tell me whether you were thinking about moving horizontally or vertically. But for the purpose of our exercise, both the first part and the second part, you would be correct if you're talking about vertical movement. Because I didn't go anywhere. I was just trotting in space. We don't want to make things too complicated here. And so if it was vertical movement, what exactly would you be looking at to be able to talk about displacement versus time? What would you be looking at in the old lady exercise? Yes, you would be looking at how many units I covered this way up. You know, you're counting. If you're looking at your graph, does my knee hit at the number 2 mark or number 3 or number 4 up and down like that per unit time per minute, or what does it do? Let's consider the simpler instance where I was resting. What would you say was the change in distance per unit time per minute when I was resting? What did you get? The change of distance per unit time. Yes, it was 0. Because when I was resting, I'm not going anywhere. There's 1 minute, but the height, if you can call it the height or the amplitude, let's call it height, for heaven's sake. Okay. My knee is at rest, so I'm not going anywhere. So the height is 0. You have 0 over time, whatever your time was, 1 minute or 2 minutes. What's 0 divided by that number? You get 0. What's another way of looking at that height and the rise and the run? What's another name for that? What do we call it in mathematics? We've called it slope. Very good. And this is the connection I was hoping you would make. We call it a slope. In calculus, we call it a derivative. Now, say it is 0. Let's take a different example. Let's say in my 80-something-year-old self, I was able to hit the number 2 mark per minute. And in my 17-year-old self, I was able to hit the number 8 mark per minute. What would you say was the change per unit time in both instances? The first instance, what did you get? It's 2. And in the second instance, it's 8. Yes, 8 units per minute or per second. I don't know how you graduated the time. So what do you conclude from this? What do you conclude? When I was slower compared to when I was faster, in terms of the derivative, which one is smaller, which is bigger? It is bigger when I'm going faster because you have 8 graduations or 8 units per minute or per second, right? And when I was 80-something-year-old, it's 2 graduations or 2 units per second or per minute. However you graduated your graph. Very good. So now you see that you can use the slope and the derivative. The idea of the derivative translates so smoothly to the idea of the derivative. So if you know how to calculate the slope, you know how to calculate the derivative. One more question for you before we end the session. Could you tell me what stood out to you in terms of the graph when I was 17 years old? When I was running like this. Your displacement time graph. And remember, this is the displacement. You're talking about the vertical motion of my knee going up and down like this. My knees. That graph compared to the one when I was going like this. Whew, and I was resting, when I was when I was really an older lady. Remember? How do the 2 graphs differ? Yes, the first graph was more, it was much smoother. It was more predictable. You could tell where my knee was at any particular moment because the change was constant, yes. But then in my 80-something-year-old self, could you really know where my knee was? Not really. Why? Because I kept stopping. I was adjusting the bandage, and sometimes things move differently when you're older. So it would have been difficult for you to spot my knee. Now, let's talk about the practical terms. Why the heck would anyone ever want to know where a knee is? And I'm not talking about we're not talking about war, we're not talking violence. We just want to be calm. I know that there's a lot of sciences out there where people target movements to figure out where things are. Can you tell me a profession in which somebody would need to know where my knee was as an 80-year-old person? Yeah, in surgery. Very good. A surgeon would want to calculate with precision. And how do you think they could figure this out? My graph is not the same as that of a 17-year-old because it's unpredictable. How would you make the displacement time graph that you have right now before you of the 80-something-year-old? How would you make it look like the one of the 17-year-old? Because now you are a surgeon. You want to make your calculations with precision. You don't want to say my knee is where it is not. We don't want to make those mistakes. What would you do? I'll give you a second to think about. What are we comfortable working with? We are comfortable with working with a displacement time graph of when I was 17 years old because it's more predictable. things are more constant. The amplitude was constant right through. What do you think we can do? What did you observe in the graph, in this displacement time graph of me when I was 80 something? Did it have some of the parts that were similar to the one when I was 17 years old? Of course it did. And those parts are easier to work with. But then there are some other parts that aren't so easy to move around. What do you think we could do? Yeah, we break them up into tiny parts so that they resemble the shape of a graph that we are familiar with. Yes, we cut them up. And this is the whole idea behind calculus, is to make those movements more manageable and more predictable. Otherwise, why would we have to worry about it? Why would we have to worry about calculus if all we had was the constant motion? Somebody's joining us here in the session in the background. Did we hear that? Yeah. Yeah. I'll see you next time. Thank you so much for your support. And let me know if you have any questions. If you want to see more of my videos, my teaching videos, you can connect with me on Udemy or here on Facebook. Just send me a message and I will be more than happy to provide you any support you may need from me. All right. Okay, let's see. Now I'm going to end this session. Let's see if I can do this majestically this time.